Okay, we're back and we're going to discuss statistics. Apparently get interrupted with an email first. Okay. So, there are two main types of statistics. There are the measures of central tendency, and then there are the inferential statistics that we can use. So we're going to start off by talking about the measures of central tendency. If we imagine that each of these little balls that I've got balanced on the little balancing scale thing represent an individual member of the group, okay? The little pendulum thing, I don't know what is that called when you've got the little balancing point? Oh, almost coming to me. Isn't that terrible when you can't remember a word you want to use? Anyway, that little triangle should be placed wherever the balls will balance, right? And that is going to tell us where sort of the average, weight is along that horizontal bar. So we've got those four balls all clustered towards the left. We've got one guy sort of in the middle there on the right, and then two that are clustered on the far end on the right. We've got to figure out where to put that triangle in the middle so that it's all balanced and nobody falls off, right? And that's going to represent sort of the point at which the balls are all sort of equidistant in some fashion from the point. And there are different fashions for us to get equidistant. The mean is when you take the average of all the individuals and then divide it by however many individuals there are. So we would add up these 7 scores, divide it by 7, and that'll give us that mean score. Now you'll notice that with the mean score, which is what the triangle is representing right now, we've got 4 on the left and 3 on the right. So clearly we're not like in the middle. We've got the triangle closer to the left end of the bar than we have to the right end of the bar. So it doesn't seem like we're at the middle of this little line. The mean is not necessarily the middle. It's going to be pulled by outliers. And so your mean might not be the best representation of like what the typical score is, or whether the scores are really clustered together or not. So that would be our mean right there. The median would be where we're trying to find the point where 50% of the scores are higher and 50% of the scores are lower. So that would be this ball right here. If we wanted a median measure, that would be really informative for things like housing prices and things where, a really expensive house could really pull up the mean housing price a lot, right? You could end up with, billionaire estates pulling up the price, so it seems like there is no such thing as something that's affordable for an average person. The median tells you, okay, 50% of houses cost more than this and 50% of the houses cost less than this. So that's kind of more informative in certain ways, right? The most commonly reported measure of central tendency is the mean. If you read research reports, they tend to report the mean. But occasionally they'll throw in the median, because if you have outliers in a data sample that is, inflating the mean score or deflating the mean score, it could be really informative to know, okay, no, seriously, this is what 50% are more than this and 50% are lower. So measures of central tendency give us this, it gives you this impression of how much the scores cluster around the center, or how similar they are, how similar they are to the average score. Measures of dispersion look at how closely the scores are grouped around whatever measure of central tendency that you have. So in this little distribution, we have 12, 13 individuals. There's one individual representing each number on the number line, and there are 2 individuals representing the number 6. So in this particular distribution, the mean would be 6, because if we added all 13 together, divided by 13, we end up with 6. The median would be 6, because 50% are below 6 and 50% are above 6. And the mode would be 6, the most common score, which I didn't put on my earlier measures of central tendency. The mode would be the most common score. So knowing that the mean, median, and the mode are all 6 makes it sound like, oh, wow, you probably have like a pretty normal distribution or something. But when you look at the actual individual scores, you're like, wow, they are all over the map. They are widely dispersed across this number line. So there's not really a pattern going on here per se, is there? It's just sort of like every number is represented, and we can't really draw any inferences from that. This is called widely dispersed data. Now, if we were to imagine that we have 13, no, we've got 11 participants, and we still have a mean, median, and mode of 6, but now we have much more closely dispersed data. They're clustering more. They're starting to form kind of that curve that you would expect with a normal distribution, right? It's still not a, there's not still not a lot of anybody on a particular number, but we're starting to see them cluster together. So that means that there's less variety, among people. The more tightly clustered the data is, the more secure we can be that our inferences about what this means for the population are likely to be correct. When you have widely dispersed data, it means, oh gosh, this could be just like a really weird sample that I pulled. So closely dispersed data is the goal. That's what we would like to see. So here's a picture of a normal distribution, sometimes referred to as the bell curve, because it looks like a bell, right? So let's attract our attention first here to the middle, and you'll notice that if you go right down the middle of this distribution, you have this little place here. The mean, if we were to add up all the scores and divide them by how many scores there are, would fall right here at this point. The mean would fall, the median would fall right here because 50% of the scores are lower than this center score and 50% are higher. And then the mode would be right here, right? Because this is the most frequent number is this one right here in the middle. So in a normal distribution, that's really the definition. The mean, median, and mode are all the same. And there are a couple of other important things to notice about normal distributions. There's always going to be in a normal distribution between one standard deviation below the mean and one standard deviation above the mean. There's always going to be 68% of people falling in that range right there, between one standard deviation below and one standard deviation above. In fact, if you go one more standard deviation out, -2 to +2, 95% of the population will fall between -2 and +2 standard deviations away from the mean. That's really an important thing to know about what a normal distribution looks like, because if you have widely dispersed data, that means you're not going to have a normal distribution. You're going to have maybe you'd have to go 3 standard deviations out to get 68% of your population in there. That's clearly not a normal distribution. Now we assume, you may have learned these things in statistics before, and you might be like, I vaguely know what you're talking about, and my eyes are glazing over. Here's why this matters. We assume that all characteristics are normally distributed in the population. Might not be normally distributed in the sample, but it is normally distributed in the population. And just about everything that's been measured in really, really large numbers that are close enough that we're starting to think, okay, we're getting a really good image of what the population looks like, almost everything is normally distributed in the population, whether we're talking about height or weight, or we're talking about IQ scores, or we're talking about average time going to bed. It's almost anything you can think of is normally distributed in the actual population. So knowing that in the general population, most characteristics that you're interested in, people will be narrowly dispersed in much more of a normal distribution, it can really give you pause. If you were to, let's see this kind of widely dispersed data, you'd realize, I don't know if I should take this study very seriously. They've got scores ranging from 1 to 12 on a scale that only has 12 items on it. Like, this is not a very good sign. We would expect, more cohesion in the scores than that. Now, there are different ways that we can process our data. So let's get a little bit into like statistics that will allow us to draw some inferences about the population. When we talk about measures of central tendency and dispersion, we're just describing the sample. That's all we're doing. But the whole purpose of collecting data on a sample is so that then we can draw inferences about the population. So once we see how the sample performed, we would like to be able to say that had I been able to measure more people or all the people, this is what I would have gotten with them also. So I can draw inferences about them. So let's start off with probably the most common statistical analysis that we do in psychology, and that is computing a correlation coefficient. There are different ways that you can compute correlation coefficients, and they allow you to use different kinds of variables and things like that. They are always represented by a little italicized r, and they represent the strength of the relationship between two variables. So I've got a couple of examples here. Job performance is the y-axis in all examples. And then on the far left, I've got surfing skill as the other variable. In the middle, I've got mechanical comprehension as the other variable. And then in the right hand, I've got alcohol consumption as the other variable. The one on the left is showing us an R value of 0.00. That means that there is no correlation between job performance and surfing skill. So clearly, this was not an assessment of job performance of surfers. This is a job performance analysis of some other job. And you can see that there's a nice circle and all the dots are sort of equally dispersed. It's just an example of like a scatter plot. But the idea is that there's no really logical place where we could put a straight line that would be equidistant from all of those dots other than just a nice flat line, right? A nice horizontal line. Now in the middle, apparently the job performance that we were assessing had something to do with mechanical ability, because look at this nice correlation between job performance and then mechanical comprehension as a separate variable. You can see that the scatter plot is going up to the right, so that's a sign that it's a positive correlation. Our R value is 0.7, so we've got this crazy strong correlation that you hardly ever find in real life. So that shows us that we have a positive correlation where higher mechanical comprehension is associated with higher job performance. Lower mechanical comprehension is associated with lower job performance. The one on the right shows us job performance and alcohol consumption. So the more alcohol a person consumes, the poorer their job performance. The less alcohol they consume, the higher their job performance. This is called a negative correlation, where being high on one variable is associated with being low on the other variable. So hopefully that's a review of something that you already knew: positive, negative, zero correlations. And this is how we process a lot of our data. When we're at the descriptive or the predictive stage, oftentimes we're going to be looking to see whether scores on two scales go together, or a score on a scale goes along with an observational count of some sort, things like that. So we're oftentimes looking to see whether two variables go together. With a regression analysis, we're going to predict one variable from another variable. It looks a whole lot like the notation that goes along with a correlation coefficient, because it pretty much is a correlation. So here we have the mechanical comprehension and job performance, which gave us that R value of 0.7 on the last slide. One of the things that a regression analysis will allow us to do is to compute that coefficient of determination, where we basically just square the correlation coefficient, and that will tell us what percent of the variance is accounted for by the predictor. So if mechanical comprehension is our predictor of job performance, and people vary on it, right? Some people are going to have a stronger correlation between mechanical comprehension and job performance than other people are. Some people are going to have like really high mechanical comprehension and really high job performance. Some people are going to have really high mechanical comprehension and sort of high job performance, right? Like people are going to vary on this. When we compute the coefficient of determination, we enable ourselves to say what percentage of the differences among people are attributable to these two variables. So of course, the job performance is the thing that's being predicted. So when we look at the coefficient of determination, we say how much of job performance is attributable to mechanical comprehension, right? That's the way you would want to phrase that. How much of job performance is attributable to mechanical comprehension? So we take our R value, so we know that they're correlated at a 0.70. We square it, and that leaves us with a 0.49. So that means that 49% of job performance in this example is attributable to mechanical comprehension. Okay. So when we do this kind of regression analysis, it allows us to establish how much of our predictor is attributable to the variable of interest. Now, 0.70 correlation coefficient, which is exceptionally high, results in a 0.49 or 49% coefficient of determination. So 49% is attributable to mechanical comprehension. Now let's be more like real psychologists and say we got a correlation coefficient of 0.3. 0.3 is considered a pretty decent correlation coefficient in most psychological research, and it will, depending on how many participants are in your sample and how, widely or narrowly dispersed those scores are, probably a 0.3 would result in a significant result. And you'd be like, wow, look, they are significantly correlated. Okay, let's square 0.3. That gives us a 0.09. When you square 0.3, you end up with 0.09, which means that 9% of the variability between people is attributable to the one variable. So let's say that mechanical comprehension and job performance had an R of 0.3. We square that 0.3 and end up with a 0.09 coefficient of determination. That would mean that 9% of job performance is attributable to mechanical comprehension. When you think about it like that, that 0.3 that came out significant in a correlation analysis doesn't seem like it's really accounting for that much in our explanatory power. It's something to really keep in mind when you look at correlation coefficient research and you see significant correlation, 0.35, and you're like, oh, that doesn't account for much of the difference between people, does it? It really doesn't. So keep that stuff in mind, that this coefficient of determination gives us a little bit of insight into how much of the variability is accounted for by the predictor. All right, the last thing that I wanted to talk about is something called meta-analysis. You're going to see a lot of meta-analyses reported in our textbook. It's a really common thing for IO psychologists to sort of look out over the field of research on this topic and do an overall review of that literature and then try and collapse the studies together into one big study and look for an overall pattern across all those studies. So it's a quantitative literature review. I look back and I explain what the research has found so far, and then I actually do my own, in my meta-analysis, I would do my own method and research results section where I describe how I lumped together all these different studies that might maybe use different variables and things like that, but I was able to lump them all together into one big study and do statistical analyses on the data from all the studies as if it was one big study. So we're going to combine the results of multiple studies. The goal being that we might get a better estimate of the true relationship among the variables of interest if we can analyze all the data together. If we can, and you might have one report that suggested a significant effect and another report that suggested that it was not significant, and another study that actually showed that there was, an inverse relationship. And you're like, which one of these is right? Well, if we can combine them all together and treat them as if they were one big study, we might be able to get sort of an overall pattern and get a better insight into what the true relationship is. So you're going to see reports of meta-analyses in our textbook, so I thought I should kind of let you know what it is. It's not collecting fresh data. It's combining data from other studies. And a lot of times they don't have the raw data. They're taking the statistical analyses that had been reported in the original research and combine them together, there's a way to do that that allows you to sort of see what the pattern is. So that's what a meta-analysis is. All right, well, that concludes chapter 2. So I will see you guys back here for chapter 3.